We're solving equations today. This is 3.5. So this is a kind of a challenging section, not because what we're doing is particularly difficult, but there's lots of different methods that you can use to help you solve these equations. And knowing which one to use can be the tricky part. So I'm going to I'll show you several different ways to solve equations. Some of these we're going to solve multiple times. And I'll try and point out some of the things that experience has taught me about, like, when I look at an equation, how do I know whether to do it by matching bases, and how do I know whether to do it by taking a log on both sides. But a lot of this is just kind of give something a try and see if it works, and if it doesn't, try something else. Okay, so this will be an assignment that when we come back and I check this on Thursday, I will not accept a blank problem on your assignment. You write down the equation, you got to try something. Okay? If all you've got is the equation and IDK, I'm not giving you points for the assignment. It's got to be done. Okay? And if anybody has looked, the assignment is all even numbered problems this time, because why? What can we do anytime we're solving an equation? What's the wonderful thing about equation problems? You can check your solution to any equation using your calculator, and we've talked about how to do that, and I'll remind you about that on at least one of ours today. So I do expect you to be checking your answers as you're going. I want you to get in the habit of doing that, because I'll be honest with you, I think about a third of the problems on the test are equations. You're going to be solving a bunch of, that's a good thing. That's a good thing, because you can check your answers to equations. You will know if you got it right or not. But make sure that we're practicing that check portion as well as the solving part, so we can pull that off efficiently on a test. So here we go. The only other big general tip is, if you're not sure what to do, if nothing jumps out to you, look for like basic Algebra 1 style things that you could do. Things like dividing on both sides or adding or subtracting on both sides sometimes come up. So check for those things as you go. All right, so let's talk through this first example here. So when I see this example, the things that I notice right away, first of all, the variables in the exponent. Okay, so sometimes we're going to see equations where the variable's an exponent. Sometimes we'll see equations where the variable's a log. This one's in an exponent. And the other thing I notice about this equation right away is it's got a 27 and a 9 and an 81, and those are all powers of 3. Right? So that leads me to think that I could probably solve this problem pretty easily by rewriting everything as powers of 3. So let's start with that step. So 27 is 3 to the third. We could write 9 as 3 squared, but what is 1 over 9? 3 to the negative squared, negative 2. And 81 may not be super familiar to you, but it is a power of 3. It's 3 to the fourth. Now, my strategy here is going to be to try and make this equation look like 3 to some power equals 3 to some other power. So there's a couple different ways I can go about this here. Most of these problems will have multiple methods of solution. Let me start by getting rid of these parentheses here. I'm going to leave this 3 to the third alone. What do the rules of exponents tell us to do to the negative 2 and the x minus 2? I'm going to multiply those. So that's 3 to the negative 2 times x is negative 2x. Negative 2 times negative 2 is positive 4. And then could I combine these two bases of 3 together? We got a rule for these exponents too. What's going to happen with these exponents? They're going to add together. So I've got 3 to the 3 minus 2x plus 4. Otherwise known as negative 2x plus 7. And then what? Division by... We can, actually, yes. And that's exactly what I would do next. Because why? Convince me that that's okay to just forget about the 3's. So if the bases are the same, then the exponents have to be the same. And this only works if you can get it so you have a single exponential on both sides. You got 2 exponentials on one side. Like here, we could not have just dropped all the 3's. We had to combine things together till we had a single base of 3 on both sides. But yeah, this is 3 to some exponent equals 3 to some exponent. The exponents have to be equal in order for that to be true. And then just a couple steps of algebra. I'll let you finish it up. And that's it. We think our answer is x equals 3 over 2. Let's practice checking. So get those calculators out. What was that method I showed you back in Chapter 2 for solving any equation ever using your graphing calculator? Do you guys remember what we did? We graph it. What do we graph? I could graph this in y1 and this in y2 and look for where they intersect. I kind of like doing it another way a little bit better, though.
But the size of the variable and with what we found as the variable, and if it equals what it equals.
Yeah, we could do that. We could substitute this in for the variable and see if it equals on both sides. I'm talking about actually solving the equation. Like if I wasn't sure how to solve it and I wanted to solve it graphically before I even had an idea what the answer was. To me, the easiest way to do it is to take your equation and get a 0 on one side and then graph the other side. Because then you're looking for where it equals to 0, you're looking for an x-intercept, right? You don't have to worry about adjusting your window to see that x-intercept because your x-axis is already in your window. Does that make sense? So if I were going to check this, I would rewrite my equation as 27, 1 over 9 to the x minus 2, and then I would do minus 81 on both sides to get a 0 on one side. And then I would graph this and look for y-intercepts. I'm sorry, x-intercepts. X-intercepts are zeros. You're looking for where that thing is equal to 0. And I'm hoping that that happens at 3 over 2. So I've already plugged mine in. And we'll graph it and wait and just hope that we get an x-intercept at 1.5. Boom, there it is. And then I can just quickly verify using second trace value. I think it's 3 over 2. Punch in 3 over 2, I get a y value of 0, so it did work. 3 over 2 gave us 0. All right, questions on that first one? Okay. Next up, what do I notice about this? So I notice that the x is in the exponent rather than inside of a log. I see a base of 3, but that doesn't match a base of 3 over here. I can't make a 45 into a base of 3. I can't make a 5 into a base of 3. At least not like in a nice simple way. We could do some simple algebra first, though. We could divide by 5 on both sides. Let's try that out and see where that gets us. Oh, there we go. We got 3 to the x over 4 equals 9. Oh, now we can get those both as a base of 3. And then we could go ahead and set the exponents equal to one another, solve, and come up with our answer. We've done these two equations, and there's something that I meant to think about before we got started. I try to remember to do this before I get started on an equation, because if I don't do it then, I'll usually forget at the end. we should always ask ourselves if there are any values of x that cannot be part of our solution, something that could cause extraneous solutions. Can you think of any values of x that could not be substituted into this equation that we just finished? Are there any rules about what kind of values can go into an exponent? So negative, we can have negative exponents, can't we? We can have positive exponents. Can we have an exponent of 0? Sure, yeah. Can you have a square root exponent? You could. It would be, it's not like, it would be kind of messy, but you could, yeah. So you can have rational numbers, irrational numbers. Yeah. So if you think about it, it's an exponential function. Just to kind of make some connections here, back to 3.1, what is the domain for all exponential functions? It's all real numbers. So there's no potential that we might have to throw something out in this if we came up with a solution here, because anything can go in for x. What about here? Same deal. Okay. Now we'll keep that in mind when we get to logs, because there are some rules about what can be inside of a log, right? All right. Let's keep going. This next one is so awesome, we're going to do it 3 times. So a couple different techniques we can illustrate with the same problem here. So a nice simple problem, 2 to the x equals 17. 17, why did it have to be 17? If it was 16, we could write it as 2 to a power, but 17, that doesn't work, does it? So again, looking through this, I noticed that the variable is the exponent and anything can go in there, so we don't have to worry about extraneous solutions. This time there is no common base. We could write 17 as 2 to a power, but that power would be really messy. It'd have a log in it. So doing this the way we did the last couple is not going to be super useful. So a couple different techniques we can do if getting a common base doesn't work out for us. We could change it into log form. You guys spent a bunch of time in 3.3 assignment translating between an exponential and log form and vice versa, right? So let's practice doing that. So a log form equation is going to be a log with some base of some value equal to something. And hopefully we're getting comfortable enough with logs that we know where all of these pieces would go in this other format. So the connections I like to make are base and exponent. What's the base here? 2 is the base. Well, you know where the base goes in the log. And in my original equation, what's the exponent? X is the exponent. Where's the exponent go here? Remember, a log is an exponent. So my exponent goes over here, which means 17 is my argument. And that's already solved. That's it. We solved it as soon as we turned it into that format. X is by itself. X is the log base 2 of 17. Done. So one step there. Change it into a log form, and we've got a solution. Now, let's say I did give you some odd-numbered problems on the assignment, which I didn't. Let's say you were working through a multiple-choice test, okay, and which our final exam is going to be. And you solved it, and you came up with log 2 of 17, and you looked at your 5 options, A, B, C, D, E. E is none of the above. And you did not see anything that matched this perfectly. What are some other answer formats that you could recognize that would be the same as this? Good. I was hoping, so log 17 over log 2 is the same thing. Who said the ln? Nice. ln 17 over ln 2 is the same thing. Right? So I hope that we're comfortable with that, like, change of base, right? We can write any log with a base as the log of the argument over the log of the base. And it doesn't matter what log base we use when we do that. So those are 2 additional formats. So I told last period's class that if they looked up their answers in the back of the textbook and they didn't get the exact same thing, to remember that there are different versions of this, but we're not going to do that because they're all even numbered problems. Sorry. I mean, you're welcome. All right. Yeah. Let's try this a different way. So this time we're going to take a log on both sides. We're allowed to do that. So I'm going to rewrite this 2 to the x equals 17, but I'll leave some space in front of the 17 this time. And we're going to take a log on both sides. And it doesn't really matter what flavor of log we take. I'm just going to go ahead with the good old common log. So we have to do the log to both sides. And what's the advantage here? What does this allow us to do with our x? So it's an exponent here. We can bring it out front as a coefficient. So this is now x times the log of 2 equals the log of 17. And we are super close to getting that x by itself. All we need to do is what? Divide by log 2 both sides. And we've got our solution. X equals log 17 over log 2, which we recognize is exactly the same as we got over here, just in a slightly different format. I want to do this problem just one more time. I'm going to do this by taking a log on both sides as well. So let me write it out, but I'll leave some space to get some logs snuck in there. But this time I'm going to be clever about my log base. So I don't have to do any division. Can you give me a log base that would allow me to just do some canceling here instead? How about a log base 2 on both sides? Because what happens when we take a log and an exponential with the same base? What do they do to each other? Cancel each other out. So we would just end up with x here, and we've got our solution as well. All right, how are we feeling?
Is there certain situations where you would use, say, the middle one and take the log on both sides rather than changing to log form?
Is there a situation where I would do this rather than this? I'm off the top of my head, I feel like anytime you can do this, you could do this and vice versa. So I would say 50 years ago, they probably didn't do this too much because, you know, log base 2 is kind of common. If this had been a different base, like a base 3 or something like that. So 50 years ago, they didn't even have calculators with log button on it, right? So they would have had to look up their logs in a table or use a slide rule. And they would have had a table for log base 10 and log base E, and they might have actually had a table for log base 2. So maybe they would have done this. But so 50 years ago, they might have done it this way just because that's what they had their tables for. Right before the fancy button on our graphing calculators, we didn't have anything except logs and ln. So we probably would have done it this way just to save ourselves the step, but I can't think of any reason that we would have to use this rather than this. Good question. Any other questions before we move on? All right, so we're going to do this one twice too. Write down that equation, and then let's do a little bit of review here. Let's do a little connection making. I want you to think back to 3.1 and 3.2 when we were dealing with exponentials. Let me cover up part of this. 10,000 times 1.06 to the x power. Can somebody give me a situation where that would be our model? What is the 10,000 representing? Population? Population, okay. So what is the 10,000? That's the initial population of people, say, in a town or something. Is this population increasing or decreasing? Increasing by how much percent per year? By 6% per year. So are we able to look at an expression like this and be able to think of this as, oh, we're starting off with 10,000, we're increasing by 6% per year? If so, that's good. That's good. All right. And what question might they be asking that would cause us to put 20,000 on the other side of that equation? Yeah, so when did that initial population grow to double its size or grow to 20,000? All right, so when we did this back in 3.2, we did it on the calculator. We're going to do it algebraically now. So we want to get x by itself. Do you see any low-hanging fruit here? Any nice simple things we could do? Say again? Chop the 10,000 by, yeah, we could divide on both sides. That would clean this up nicely, wouldn't it? Get x a little bit more by itself. So let's divide by 10,000 on both sides. That gets us 2 equals 1.06 to the x power. And let's go ahead and write that down twice. And I would like you to look at our examples up above and please solve this twice using 2 different methods that we did up above. I would recommend one of your methods be change it to log form. And then the other one take a log on both sides. Whether you want to do just a common log or an ln on both sides. We haven't done one where we did ln on both sides. That might be a good idea. I think I'm going to do one of mine that way. So we may end up with different formats of the same answer, but if we typed our answers into our calculator, we should come up with the same decimal approximation. Of the 2 that I've got on my paper, which one do you like better? This is totally just a judgment call. You like the one on the left better?
If I want to calculate the exact value, the one on the right is a lot quicker to get there because you don't have to then put it back into change base.
This would be faster, yeah. This we'd have to use change of base formula, or we'd have to hunt through our menu to find that thing. But that doesn't take too long. I'm not a huge fan of that 1.06 base. I don't know. That just kind of makes me feel a little... I'm used to seeing bases that are like integer values, but they're both the same though, right? So, and when it comes to like which one's going to earn you more points on a test, the answer is yes. Both. Like, they're both good. They're both fine. Math alpha math. Yep. All right. Let's keep going. Let's look at some that have logs in the equation. So a couple ways that we can solve equations that have logs. So when I look at these 2 equations, actually it's the same thing twice. When I look at this equation, the first thing I notice is where my variable is. It's inside of a log. And I need to be kind of careful here because the inside of a log has some rules about it. We need to make sure that whatever x ends up being, we don't end up with a negative or a 0 in here. So what's the smallest that x could be? Or what's the biggest number that x cannot be? -1. X has to be bigger than -1, agreed? Because the inside of this has to be bigger than 0. So x would need to be bigger than -1. It can't be equal to -1 either. because we can't take the log of 0 either. So we'll keep in mind, actually it might be smart of us to write that down kind of down here where our answer is going to end up. X is greater than -1, just so we don't forget to check that at the end. And if we do get a solution that is less than or equal to -1, we'll have to toss it out. It would be extraneous. So when I get an equation like this that just has a single log on one side and then a number on the other side, I like to change it into an exponential. So let's try that. So we practiced this a bunch. We're going to have a base, and we're going to have an exponent on that base, and it's going to be equal to some value. So if I look at the original equation, what is the base? The base is 3. And what is the exponent in the original equation? A log is equal to an exponent. A log is an exponent, so the exponent is 4. And then my value is x plus 1. And that's a pretty simple equation. 3 to the 4th equals x plus 1. 3 to the 4th is 81. So x must be 80. And 80 is greater than -1, so we'll keep it. So there's another way to do this. I'm not a huge fan of this, but it can be done. Do you guys remember a minute ago when we had like 3 to a power equals 3 to a power, and we just said, let's ignore the 3's? Well, we can do that in reverse. We can stick a base underneath anything. So, so if these two things are equal, then I can pick whatever base I want, put a 4 as an exponent on one of those bases, and put a log base 3 of x plus 1 on the other base. What would be a nice convenient base that we could use for this? 3 would be nice, right? Because what's the 3 in the log base 3 going to do? Cancel, and we're just going to get x plus 1 equals 3 to the 4th. So x plus 1 equals 81. So x equals 80 again. So the same way we can kind of drop a base off and just look at the exponents, we can take an equation and force both sides to be exponents on the same base. That's the legal move. All right. We doing all right? Well, so far, so good? Okay, that's awesome. I want you to remember this part where you felt really comfortable, okay? And hold fast to it. Okay? Because now it's going to get interesting. So, and this is going to be one of those things. So let me give you a little preface to this. What we're going to talk about next is something that's not going to go away, okay? So this is something we're going to see in second semester. So a lot of times we get to this point in our chapter 3 and my students are like, you know what? I'm just not going to bother learning that and take that 5% hit on my test. I'll just make sure I got everything else down and I'll ignore this thing. And that's not a good strategy because you will be using this again next semester. So, okay, now it's not a big deal, okay? It's one of those things. I know I'm making it seem like a big deal, but hopefully when I show you, you'll be like, he made a big deal out of nothing, okay? So let me show you a couple equations. Before we get into this, I think this might help you a little bit. I didn't do this last period, and I feel like I should have. All right, don't worry about writing this down. Just set your pencils down and watch for a second, okay? Try and soak this in. X squared plus 2x minus 5 equals 0. What type of equation is that? That's a quadratic equation. And if I asked you to solve it, there would be kind of 2 or 3 options we'd look at. We would hope that we could do what? What's the easy one? We hope that we could factor, set each factor equal to 0 and solve it. This one doesn't. So our fallback plan is quadratic formula or solving by completing the squares, which we didn't talk about, but I know some of you know how to do that. Right? So those would be our options. And we've done this and we've practiced it over and over and over again. And if we're not good at those things yet, we really need to be here soon. Okay, so this is a quadratic equation. Agreed? Yeah. Okay. Let me show you an equation that you're going to see next year, or next year, also next semester. Sine squared x plus 2 sine x minus 5 equals 0. Okay, we're going to see some equations like that next semester. And I want you to recognize that this is also a quadratic equation. For the same reason that this is. This is a quadratic equation because it's something squared. We've got a squared term, we've got a linear term, and we've got a constant term. And the thing that's being squared here is the same thing that's over here, right? Now, we haven't seen this notation yet, but sine squared x means the sine of x squared. It's just a shortcut for writing that. But do you agree that I have something squared and then that same thing over here not being squared, and then a term that doesn't have that thing in it? So we can solve this by factoring the quadratic formula just the same way we can this. There's a little bit of an extra step in this where we have to deal with that sign, but I'll show you how to deal with that. It's not a big deal. The big challenge for us is just going to be recognizing that sometimes we have some weird looking stuff that fits into a quadratic form. Okay? Here is another type of equation that I would say is in the quadratic form. You guys ready? Let's see here. Sorry, let me try it over again. 3 to the x squared plus 2 times 3 to the x minus 5 equals 0. Can you look at that and see how it is something squared? And then you have that same thing that's not being squared. This is like my linear term. And then we have a constant term that does not have that thing in it. So this is a quadratic equation. And we can solve this by factoring or by using the quadratic formula. Well, how can I have to deal with this messiness that's on the inside? But I'm going to show you how to do that. Okay? So the next 3 examples we're going to do are going to be all quadratic type equations, although they may not initially look like it. They will be quadratic type equations. And I'll show you how you're going to recognize that they are as we're doing them. So here's the first one. I am hoping that when you see this, that this one kind of jumps out as a quadratic equation to you. After the setup that we just did, does that kind of look like a quadratic equation to you? Go ahead and write that down for me, please. This first one. Don't worry about this other one that I'm changing as we speak. We'll come and do that in a minute. Pay no attention to that equation. So what I notice when I look at this is that I have my variables are in the exponents, but I got the variable in more than one place. There's more than one exponential here that has an x in the variable. Now, we've already dealt with some equations that have variables in the exponent, but in those equations, there was always only one thing that had a variable with an x in it. This time, we have multiple things with a variable with an x in it. This is going to lead me to believe, just from experience, that this can probably be thought of as a quadratic. And this one's pretty straightforward, that it looks like a quadratic to me. All right. So my first question is, can you look at that and kind of squint your eyes and forget about the fact that this is a 2 to the x and see a quadratic equation here? That's the biggest hurdle to get over. Are we feeling okay about that? All right, now let me show you how to deal with this. Like, we can deal with quadratics, but when you start throwing weird stuff like 2 to the x in there, it gets pretty messy. So check it out. We're just going to take this messiness and we're going to hide it behind a different variable, which I'm going to call w. So off to the side here, you're going to write let w equals 2 to the x. They often use w and u and v when we're doing this particular technique. This happens quite a bit in math. Okay, higher level math. And calculus next year, you'll learn this thing called UV substitution. I think it's UV. Okay, so here's what I'm going to do. So I'm going to let w equals 2 to the x. So I'm going to come back to my equation, and every place that's a 2 to the x, I'm going to replace it with a w. So this big, nasty-looking equation just becomes w squared plus 2w minus 8 equals 0. Yeah, I like that. I like that analogy. I'm basically storing 2 to the x into w, so I don't have to think about it, right? It is, isn't it? Like, I can actually wrap my head around this. This hurts my eyeballs. This is something that, like, we've done. We've done this a million times. And I think this factors too, right? It does factor. So let's solve this by factoring. And folks, again, we are at the point that you should be able to factor this quadratic in like 10 seconds or less. And if you're not there, you need to get there soon, okay? I'm not messing around. If you walk into a calculus class next year, wherever you are, and you still can't factor a simple quadratic like this, it's going to be a rough year for you, okay? You should not be using the quadratic formula to solve an equation this simple. All right, so this factors into, it's going to be 2 and 4, and they need to add up to positive 2, so I think we want a positive 4 and a negative 2. All right, and then we'll show the next step. I wouldn't normally write this down if I were doing this, but let's show the reasoning behind this. Zero product property says that we can take our factors and split them up and set them each equal to 0 and solve them individually. We get w equals 2 and w equals negative 4. So that's all fine and good, but we're not solving for w, we're solving for x. Once we get w down to a value, or 2 values, or 3, whatever it ends up being, then we go back and back substitute the thing that we were kind of hiding from before. We were hiding away from this 2 to the x power, and we put that back in. So I get 2 to the x equals 2, and 2 to the x equals negative 4. And then I'll just solve those 2 equations, and we're done. So this first one here should be pretty straightforward. I don't think we need to do any algebra here. Just use your brains. What exponent can I put on a 2 to make it equal to 2? X must be 1. This next one's a little trickier. What exponent can I put on a 2 to make it equal to negative 4? That is a good question. Is it a point something? Like a half? 2 to the 1/2 would be the square root of 2. That's never going to give you a negative. A lot of you have the correct answer, which is it can't be done. There is none. Now, let me convince you. I'm going to take this and take a log on both sides. Log of 2 to the x equals log of negative 4. And what's wrong with this picture? We can't do log of a negative number, right? We know that we can't do that. There's no way to take a positive number, put an exponent on it, and make it negative. So there is no solution for this part. This would be undefined. So for this, there is no solution that comes out of it, but we were able to get a solution out of the other one. 1 is our answer. We could go back and plug it in and make sure that it works, and it certainly does. So the whole idea here is we got something that we know is a quadratic because it kind of looks like 1, but it's a whole bunch of messy stuff inside of the quadratic. So let's take the mess out of it. Let's pull the mess out and substitute just a single variable in place of it and deal with this simplified version of the problem. Once we solve that, then we can stick the mess back in and then solve again. You get kind of the concept? So I was showing you a minute ago that we were going to see an equation like this. What do you suppose we're going to let w equals in this one? We're going to let w equal sine of x, and then we'll solve for w, and then we'll come back and we'll put that number in here and solve this, okay? So this is something that we're going to see quite a bit, okay? Now, here's the trouble. Sometimes it doesn't look so much like a quadratic equation. So here's our second example here. I'd like you to write this down. Now, I look at this, that says variable in the exponent in multiple places. It was actually the same note that I had on the other side. When I look at this, I notice that my x's are in the exponent, but they're in 2 different exponential pieces. So common base isn't probably going to help us here because these things are being added together. There's no way for us to get them squished into a single exponent. So I'm going to guess that this can be written as a quadratic, but we're going to probably have to play around with it a little bit to make it. Now, one thing I noticed is that these bases aren't the same, but we could make them the same, couldn't we? 4 is the same as 2 squared. That'd probably be my first move. Now 8 can be written as 2 to the third. Do we want to do that, or we want to leave it as 8 for now? Oh, you want to do minus 8 on both sides so we have equal to 0? We can do that. Are you guys comfortable doing that in the same step? Okay. I like what you're thinking. You're thinking, okay, if this is going to be a quadratic, we might as well get that 0 on one side. You want to write it as 2 to the third instead of 8? We'll do that in the next step. I don't want to get too much going on here. We could do that, yeah. Let's think here. Well, I'll just go ahead and write this down. 2 squared to the x. Actually, I'm just going to make that 2 to the 2x. Right? It is 2 to the 2x. I don't know if that's helpful or not, but we'll give it a shot. Minus, you said make that into 2 to the third. Okay. So we got all the bases the same. It'd be awesome if we could combine them all together into a single 2 to a power, but they can't do that with pluses and minuses. Sorry. So I want to try and make this look like something squared plus maybe something and then something else not squared and then maybe plus or minus something equal to 0. What are you thinking? The question is, can we just add these two exponents together? We could if this was multiplication. That's exactly what we would do. But with addition, there is no rule like that. I like that you're thinking that. You want to call this 2 to the x? Yeah, that would work. So then this needs to be 2 to the x also. So we got to get that 1 off of there. How could we rewrite this? There we go. There we go. We practiced this day 1 of this unit. You guys in what situation would we ever add two exponents? We do that when we are multiplying. So I'm going to rewrite this as 2 to the x times 2 to the 1. Are we okay with that? And what if I took this 2 to the 1 out in front? That's just a 2. Convince yourself that this right here is the same as what we started with. 2 times 2 to the x. Exponents 1 here, exponents x here. 1 plus x is, does it work? All right. And I'm going to say, why don't we just turn this back into an 8? Because this is starting to look like a quadratic to me now. And then we would go and solve this. Except we don't need to because we just did. This is the same problem that we've already done. Isn't it? Same thing we just did, we just had to do a little bit of work to get there. Okay, so they're usually not going to lay it out for you and make it look like a quadratic. A lot of times they're going to give you something where you're going to have to kind of do some work to make it look like a quadratic. Okay? Now, how did I know to do this? This is the big question. My students are always like, how did you ever know to do this? And it's just because I've done hundreds of these problems, and I know that most of the time when I get something where I've got exponents and two different things and it's being added together, I'm going to have to try and turn it into a quadratic or some other kind of fancy type of equation. Okay, the ones that you're going to see in this chapter will be quadratics because we're trying to set you up for those types of sign equations that I was showing you a minute ago. All right, so I would love for you guys to give one of these a try, and I have every faith that you can accomplish this. This one is not quite as straightforward as the first one that we did, but it's much more straightforward than the last one that we did. So we're looking at this. We see x's that are in our exponents, but they're on different bases, adding and subtracting. Well, I should say they're in a different term. They're in a different term, yeah. So there's no way we're going to be able to get those together into a single base of 2, but maybe we can squeeze it into that quadratic form. And what I'm thinking is maybe 2 to the x again, right? Because I think we can make this as 2 to the x squared, can't we? So there'd be my first step. And it looks like a quadratic, but it kind of hurts my brain, so let's take the complicated piece, 2 to the x, and hide it behind w, just temporarily, just so we can wrap our heads around it. Oh, by the way, sorry, can we make this a positive 20 over here so this thing actually factors? I'm sorry.
I like that a lot better, thank you.
I'm sorry, I know. We will deal with quadratic formula momentarily, but I don't want to do it right now. Oh, good. I need to change my notes for next period so I don't forget that again. Bless you. All right, so once we've done that, then we get w squared minus 1w minus 20 equals 0. And that factors. Huzzah. Am I making that an exponent? And remember, there's a number of different ways to solve this equation. If you look back in our notes, we did something very similar to this. We did it 3 different ways. So honestly, I'm not too sure why I did all that work. I should have just rewritten this in log form. That's way easier, isn't it? The log base 2 of 5 is equal to x. That would have been on 2 less steps. Same thing, same thing. Less steps.
I did what you did with log.
Yeah, I tend to use ln's instead of logs because it's less writing. You can save whole halves of seconds. All right. Folks, you guys are doing pretty well with this. I'm not seeing that deer in the headlights look for most of us that. And now this is getting, I mean, this is big kid math right here. Like we're taking some pretty weird looking equations and forcing them into some like pretty weird looking forms so that we can do like some quadratic stuff to them. I do want you to keep in mind though that when we're working a problem like this, the bulk of the work from here to here, this is Algebra 1 level. I mean, this is basic. All we're really doing is recognizing a quadratic form, sometimes doing a little work to force it into it, and then hiding the messiness behind some this is kind of the key thing that I'm teaching you, really, with this couple examples. So we're going to do one more. This will be probably one of the most challenging equations we'll solve all year. You are going to see a problem like this in your assignment, and I chose this one so that you could follow our steps exactly and come up with a solution. And I love it that you're already thinking about the simple things that we can do. That's great. So my first inclination is I could multiply by 3 on both sides and make this look a lot simpler, right? That would be my first step. So before I start looking too deeply into this, let's clean it up a little bit, make it look a little bit nicer. 2 to the x minus 2 to the negative x equals 12. And when I get to that point, I'm like, okay, there's 3 terms there. And there's x's in 2 different of those terms as an exponent. Yeah, this is probably going to be a quadratic. It's just, the question is, how do I make this into a quadratic? Yeah, I'm thinking that 12 is probably going to, we're going to need a 0 on one side. Do we want to go ahead and take care of that right now? All right, sure. 2 to the x minus 2 to the negative x minus 12 equals 0. We could factor a negative out of our coefficients. That would make this one negative. We can't factor a negative out of an x. No, I can think of this as negative 1 times x. Say again. We could. 2 to the negative, well, it would be 2 to the negative 1 and then to the x. I could rewrite that as, this could become 2 to the negative 1 to the x power, or 2 to the x to the negative 1, which might be helpful. How about this one? 2 to the x to the negative 1. Do you like that? Let's answer a question here first. Yes? Great question. If this had been multiplied here, so if these had been multiplied, then we would add these 2 exponents together and they would become a 0. Yes, but this minus here, if the plus or a minus here messes that up. So your instinct is right. If you can combine these 2 things together into a single base, that's the way to go. As soon as they put a plus or a minus in between, that throws that out. So I kind of like, I did this a slightly different way last class. I kind of like this. I'm going to go with this for this one. So I got 2 to the x minus 2 to the x to the negative 1 minus 12 equals 0. Is this going to work? I've never done it this way. There's nothing being square, but check this out. All right, so here's what I think this might clear it up if I write it this way. No? No better? You don't like this? I'm gonna do some fraction busting. Fraction bust? What would I multiply everything by to get rid of my fractions here? I'm working to get rid of my negative exponents. I don't like this negative exponent. This is, when I saw this, I was like, how can I get rid of this? So I changed it into a positive exponent, but that gave me fractions. What can we can do that, but answer my question though. What could I fraction bust with? What would I multiply by? 2 to the x. I kind of like to make it look like a quadratic before I start substituting stuff in. So 2 to the x times 2 to the x, that's 2 to the x plus x. And this, what's 2 to the x times 1 over 2 to the x? 1. And 2 to the x times negative 12 is just negative 12 times 2 to the x. That's looking like a quadratic because x plus x is 2x. There's our 2 to the x squared. Oh, hang on. Sorry, I'm getting ahead of myself. I'm excited here. 2 to the 2x. I'm going to rearrange this and put the negative 12 times 2 to the x next, and then the minus 1 at the end. Ooh, we're getting there. It would not. Great question, though. This 12 has its own exponent. If the bases don't match, we can't combine them together. Yeah, super common mistake, though. So here we go. 2 to the x squared minus 12 times 2 to the x minus 1 equals 0. That looks like a quadratic to me. That was messy. That was a whole bunch of steps. That was icky. Well, we'll get there in a second. Let me show you what we did last class. Can I show you guys this? This is a little bit quicker. So I just multiplied by 2 to the x from the get-go. And then we ended up with a 2 to the 0 when we did that. I mean, it still took us several steps to get there. Multiplying by 2 to the x is kind of the key, though. So, all right, let's finish this up. So let's hide that 2 to the x behind a w. And I apologize that all of my examples of this have been 2 to the x. It's not always 2 to the x. Sometimes it's 3 to the x or 5 to the x. So I'm sorry for being so boring with these, but that's all right. You'll see some others in your assignment. And that does not factor, so our old dear friend, quadratic formula. Bless you. Da-dun-dun. Here's another Algebra 1 skill that I'm really hoping that we're getting confident with. Don't just copy my work down, guys. Do your own quadratic formula here. $144 plus 4. 48. 48. 4 goes into 148. Is there anything bigger? 4 and 37? Hi. Yeah. For you. It's not one of the pink ones, so I don't think you're in trouble. The pink ones don't always mean you're in trouble, right? Usually, yeah. All right, pink ones just mean you're going to the main office. It could be to get an award, you know? So they are. I don't think I've ever seen, I think they usually go to the office. So W equals 6 plus root 37. Are you guys coming up with 6 plus or minus root 37? Please. So we got both here. 6 minus root 37, 6 plus root 37. And instead of writing W, I'm just going to write 2 to the x because that's what W was, right? So 2 to the x is 6 plus root 37, or 2 to the x is 6 minus root 37. And thank you. One of those I'm going to throw out because it's negative. Which one's negative? 2 minus root 37. It's negative. It's barely negative, but it is negative, right?
36 is 6, so that'd be less than 6.
Yeah. But this is negative, so this will be a nope. So since that's negative, we'll throw it out. So then we just need to solve this. And I'm going to go the easy way and just write it as a log equation. It would be exponent is x equals the log, my base is 2, and the value is 6 plus root 37. I could accomplish that by taking a log base 2 on both sides, or doing an ln on both sides, or a log on both sides. We'd get to the same answer. Whew, that was fun. So, I think there's one or two like this. So, and we showed, we showed more steps than we needed to here. This is notes. So, you guys, you'll be able to do it. All right, what questions do you guys have? Now, keep in mind, the main part of this lesson is not nearly to that level. So looking back at these now, like, these are probably going to look pretty simple to you. You guys got this. All right, you got the rest of our time here. I'll put the assignment up on the board, and you can get started.